This video is brought to you by mywayteaching.com.
If you continuing the electrostatics of conductor, the fourth important point is electrostatic potential is constant throughout the volume of the conductor and it has the same value on its surface. Since E is 0 inside the conductor, it has no tangential component on the surface. No work is done in moving the smallest test charge within the conductor and even on its surface, which means there is no potential difference between any two points inside or on the surface of the conductor. So if the conductor is charged, electric field normal to the surface exists. This means potential will be different for the surface and a point just outside the surface. So in a system of conductors of arbitrary size, shape and charge configuration, each conductor is characterized by a constant value of potential. But this constant may differ from one conductor to the other conductor, but it is same in a single conductor. And the fifth important point is electric field at the surface of a charged conductor. See, E is equal to sigma by into n cap, where the sigma is the surface charge density and n cap is a unit vector normal to the surface in the outward direction. So in order to derive the expression for this, we choose a pillbox, which is nothing but a short cylinder, as you can see in this figure, as the Gaussian surface about any point P on the surface, and the pillbox is partly inside and partly outside. Surface charge density, surface of conductor. Okay, you can consider this pillbox is partly inside the conductor and partly outside the conductor, and it has a small area of cross section that is given by delta S, okay, and negligible height. Just inside the surface, the electrostatic field is 0. Just outside the field is normal to the surface with magnitude E. Thus, the contribution to the total flux through the pillbox comes only from the outside cross section of the pillbox, because inside obviously it's 0. So that flux is equal to plus or minus E into delta, or else we can take plus or minus E into delta S. So over a small area delta S, E may be considered constant and E and delta S are parallel or anti-parallel. The charge enclosed by the pillbox is given by sigma into delta S. This is charge enclosed. Okay, so by Gauss law, we can write E into delta S is equal to sigma delta S by epsilon naught. E is equal to sigma by epsilon naught. So including the fact that electric field is normal to the surface, we get the vector relation, which is true for both signs of sigma. If it is greater than 0, electric field is normal to the surface outward. If it is less than 0, then electric field is normal to the surface inward. Electrostatic shielding. What is this electrostatic shielding? Consider a conductor with a cavity, as you can see here, with no charge inside this cavity. A remarkable result is that the electric field inside the cavity is zero, whatever be the size and shape of the cavity and whatever be the charge on the conductor and external fields in which it might be placed. Inside the cavity, that electric field is zero, whatever may be the remaining conditions. And we have proved a simple case of this result already, that is the electric field inside a charged spherical shell is zero. But the vanishing of electric field in the cavity of a conductor is a very general result. A related result is that even if the conductor is charged or charges are induced on a neutral conductor by external field, all charges reside only on the outer surface of the conductor with cavity. Even if you induce, they remain on outer surface of cavity. Whatever be the charge and field configuration outside any cavity in a conductor remains shielded from the outside electric influence. The field inside that cavity is always zero. This is known as electrostatic shielding. Okay, and the effect can be made use of in protecting sensitive instruments from outside electrical influence. Okay. Some important electrostatic properties you can see here. Cavity inside the potential is constant and the electric field inside a conductor is zero, and at the surface the charge is given by, electric field is given by sigma by epsilon naught n cap. Now let us see a simple example. A comb run through one's dry hair attracts small bits of paper. Why? What happens if the hair is wet or if it is a rainy day? Remember, a paper does not conduct electricity. B. Ordinary rubber is an insulator, but special rubber types of aircraft are made slightly conducting. Why is this necessary? C. Vehicles carrying inflammable materials usually have metallic ropes touching the ground during motion. Why? A bird perches on a bare high power line and nothing happens to the bird. A man standing on the ground touches the same line and gets a fatal shock. Why? Why? So, these are the natural things that we see in our day-to-day life. What is the reason? Let us see. For the first comb case, why the comb attracts paper? That is because comb gets charged by friction. We already studied this. The molecules in the paper gets polarized by the charged comb, resulting in a net force of attraction. If the hair is wet or if it is rainy day, friction between hair and comb reduces obviously the comb does not get charged and thus it will not attract small bits of paper. Okay. And the second part, why the rubber is made slightly conducting in aircraft, to enable them to conduct charge to the ground, as too much of static electricity accumulated may result in spark and it result in fire. For the same reason, vehicles carrying inflammable materials, they have metallic groups. And for the fourth part, current passes only when there is a difference in potential. A human is on the ground. When he touched that, the line, current line, the potential difference between the ground and that is, it forms a potential difference. Electricity flows to the ground. But when that board is standing, it is on the same line with there is no potential difference, so there is no flow, electricity flow, no shock. That's it. Now let us study dielectrics and polarization. We already know what are these dielectrics. These dielectrics are non-conducting substances. In contrast to conductors, they have no charge carriers. They are non-conductors. See, when a conductor placed in an external electric field, the free charge carriers move and charge distribution in the conductor adjusts itself in such a way that the electric field due to induced charge opposes the external field within the conductor. This happens until in the static situation the two fields cancel each other and the net electrostatic field in the conductor is zero. In a dielectric, this free movement of charges is not possible. It turns out that the external field induces dipole movement by stretching or reorienting molecules of the dielectric. So the collective effect of all the molecular dipole movements is net charges on the surface of the dielectric, which produce a field that it opposes the external field. Unlike in a conductor, the opposing field so induced does not exactly cancel the external field. It only reduces it. The extent of the effect, it depends on the nature of the dielectric. So to understand the effect, we need to look at the charge distribution of a dielectric at the molecular level. Okay. See, the molecules of a substance may be polar or non-polar. In a non-polar molecule, the centers of positive and negative charges coincide. The molecule then has no permanent dipole moment. For example, O2, H2. The centers of both, they coincide, positive and negative. Because of their symmetry, they have no dipole moment. On the other hand, in case of polar molecule, in which the centers of positive and negative charges are separated even when there is no external field. So such molecules have a permanent dipole moment. For example, HCl, H2O, these are all polar molecules, isn't it? You can see here, this is a conductor and a dielectric. Difference in behavior of a conductor and dielectric in an external electric field. And polar and non-polar molecules, H2, CO2, non-polar, HCl, H2O, where centers of positive and negative, they are separated by a distance. They do not coincide in case of polar molecules. Okay. Dielectric develops a net dipole moment in an external electric field. First, we are considering non-polar molecules and then polar molecules. See, in an external electric field, the positive and negative charges of a non-polar molecule are displaced in opposite directions. Isn't it? You can see here. The displacement stops when the external force on the constituent charges of the molecule is balanced by the restoring force due to internal fields in the molecule. And the non-polar molecule thus develops an induced dipole moment, and the dielectric is said to be polarized by an external field. See, when the induced dipole moment is in the direction of the field and if it is proportional to field strength, the induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of external field. If you consider a polar molecules, a dielectric with polar molecules also develops a net dipole moment in an external field, in presence of external field, but for a different reason. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation. So the total dipole moment is zero in that case, in the absence of external electric field. But when there is an external electric field, when we provide external electric field, the individual dipole moments, they tend to align with the field. First, they align randomly, as you can see in this figures. But when we apply external electric field, they tend to align, uniformly in the direction of electric field. When summed over all the molecules, there is a net dipole moment in the direction of the external field. The dielectric is polarized. The extent of polarization, it depends on the relative strength of two mutually opposite factors. Okay, and the dipole potential energy in the external field tending to align the dipoles with the field, and thermal energy tending to disrupt the alignment. There may be in addition the induced dipole moment effect as for non-polar molecules, but generally the alignment effect is more important for polar molecules. Okay. Thus, in either case, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of external field. The dipole moment per unit volume, we call it as polarization. It is denoted by P. Which is given by, for linear isotropic dielectrics, P is equal to Hc into A. This is a constant of the dielectric. This is known as electric susceptibility. Okay. Of the dielectric medium. It is possible to relate this dielectric susceptibility to the molecular properties of the substance.